Evaluating surface integrals over arbitrary surfaces with an arbitrary shape is in principle pretty easy. So just take a sheet of paper with a grid. So here you have a surface with an arbitrary shape. It can be divided into very small surface elements, and actually we will see that surface integration is just summing over these small surface elements. So let's have a look at this problem. So if you think that our grid paper sheet with the grid is here, so it may be a curved shape, so it's not flat in this case in general, then you can divide it into small squares, which you can say that this is a surface element, and so the total area here is, or total surface is S, and it has a total area of this surface S is A. So it's very obvious that the total area is just a sum over all these elements. And in the limit of infinitesimal surface elements, this sum goes to integration over the surface. And now, by definition, actually, the total area of the surface is just the surface integral over the surface. But now here we just don't have any function over which we are taking the integral. So integration is simply summation over vanishingly small terms, and also integration over surfaces is summation over small elements. And this is how numerical integration is performed. But note, in this case, we have no function which is integrated over the surface. So it's just a summation over all the surface elements. So let's develop this idea further and look at the concept of flux of a vector field. So how to define flux of a vector field? So let's take a practical example. We have here a river flowing with a velocity v. Actually, this is a vector field because the velocity is dependent on position. So you may have a fast flow somewhere and a very slow flow somewhere else. And now if you have a net here, for example, for catching fish, so you could look at the flux or flow of water through these small surface elements. So actually we could look at this, divide this net into small squares, and so each of these has an area delta A, and now there's a unit vector pointing to direction which is perpendicular to the surface, or this level of this square. And so we can define that we have a surface element vector, which is the area of the element times the unit vector pointing the direction which is perpendicular to the surface. And so if we look at the flow of water through these small elements, which start from volume flow, and volume actually is cross-sectional area times distance in direction perpendicular to the surface, so the time derivative. So the amount of volume in a certain time interval is just this area element times the rate of change of position, and that is actually area times the velocity in perpendicular direction of the surface. So we can divide the volume flow through a small area, or any area, that is area times velocity. But if we have an arbitrary shape of surface, or the velocity is position dependent, so what is actually the direction of the flow, and what is the area of the net? So we need to look at the flow through the small elements. So we define, well, actually we look at flow through a surface element and define flux or flux element. So if you look at the first of all the velocity, that can be divided into two components. There's this velocity perpendicular plus parallel, and this perpendicular is parallel to the unit vector of or directional vector of the surface element. So actually, so if you define the flux through the surface element as the perpendicular velocity times area, so it's like this. So it's just flux is a perpendicular component of velocity times the surface element, and this can actually be written as velocity dot product between velocity and the unit vector times the surface area. So this is actually a dot product between the velocity vector times the surface element vector. And now that is just like the volume flow through this small surface element. So if you like to calculate the total volume flow through this net here, so you have to sum over all these surface elements. So there's a flow through this small grid, or this square, or this opening and this opening. So actually the total flux is sum over these elementary fluxes, and so it's actually the sum over perpendicular velocity times the surface element, and so it's dot product between velocity and the surface element. And if we go to the limit of an infinitesimal area, then flux is actually surface integral over dot product between velocity and this surface element. So formally you can define the flow or flux of this volume flow as a surface integral of this velocity vector, and it's a dot product between this velocity and surface element. So it can be also thought that there's a perpendicular component of velocity times the surface element, and then you sum over all these elements. And this can be applied. So this is actually the flux of flux phi of velocity field v through surface S. And if we need numerical integration, this is just simply summation over all these elements, and which gives a total flow. And this is what happens in the case of numerical integration. And this is applicable to any vector field. So as we do in our course of electricity and magnetism, electric flux through a surface S is actually defined as surface integral of electric flux density times the surface element. And in principle it could be thought as a flux element, this perpendicular component of flux density at a certain chosen surface element, and so it's a sum over all these elementary flux, like flux elements. Sorry. So a very simple example here is the electric flux of a point charge, and in this case we have a spherical symmetry. And so if we define a surface which is a sphere with a radius r, so that the charge is in the middle of the, just in the center of the sphere. So this is a spherically symmetric case. So the field lines point outwards from the charge, and of course when we rotate space to any direction, so the flux density does not depend on the position on the surface. So spherical symmetry implies two things. First, electric flux density points to the direction of any surface element, and now electric flux density is constant, or its magnitude is constant at constant distance r. And so if we look at the flux element, so this since this dA is just the unit vector of the area of the surface element, so the flux element is just the flux density dot the surface element. On the other hand, it's just the d dot n, and since d and n are in the same direction, so this is just flux density, magnitude of flux density d and times dA. So the electric flux is just the surface integral, or the closed surface in this case. So this sphere here denotes a closed surface. And according to this spherical symmetry, so that d points to the same direction as this unit vector of any surface element, so this dot product can be moved to transformed into a scalar product. So there's just magnitude of d times dA, and since the flux density is constant on the surface of integration, we can take the flux density out of this integral. So it's just d times the integral dA over the surface. And this is of course the total area of the surface. So this is just d times a. And if radius is r, so this is just d times 4 pi r squared. And so here we have the electric flux is flux density times 4 pi r squared. So on the other hand, we defined electric flux as the total charge inside a closed surface. So it's just this point charge q, and so we can hence solve. We can equate these two ways to write the total flux, and so actually this flux density is just the charge divided by 4 pi and radius squared.